Hello, this is video number 11. I'm going to go over free fall in this video. This is an extension of the previous video where we learned how to use the kinematic equation, so make sure to watch the previous video if you haven't already. So objects in free fall are any objects moving under the influence of gravity only. So we ignore air resistance, drag, any other forces. The only thing acting on the object is gravity. So if that's the case, then we know that the amount of acceleration on the object is the acceleration due to gravity from the Earth pulling it downward. So the magnitude of this acceleration is always going to be 9.8 meters per second squared, and we represent it with the lowercase letter g. This is always a positive number because this is just the magnitude of the acceleration, the amount of the acceleration. Now, if you're trying to know the acceleration of the object, which is a vector, then you need a direction. So the acceleration is going to have to include a negative. So the acceleration will be negative 9.8 meters per second squared because this acceleration is downward. So over here I have a picture. It's supposed to be an animation, but if you have an elephant and a feather and they're falling from a building, if you could ignore air resistance, then they would actually both reach the ground at the same time. There's actually a video on YouTube you can find where there's an astronaut that actually drops a hammer and a feather on the moon to show you that in the absence of air resistance, they actually do reach the ground at the same time. So for all objects that are in free fall, we are going to use the kinematic equations because they're going to be under a constant acceleration, which is going to be the negative 9.8. And that was the requirement for using the kinematic equations. We are going to have two major cases of free fall. The first one is an object being dropped. So if you're told that an object is dropped or released from rest or is just falling, then you're going to assume that the initial velocity is 0 meters per second. So the problem may not tell you that, but this is a known variable, so it will be one of your givens. And you will always know that the acceleration is negative 9.8 meters per second squared. Even though it's not given in the problem, this is one of the givens that you will write down. I do have a couple of notes. So the first one is that the final velocity is not 0. So this is because a lot of times you're going to have an object falling, it's going to reach the ground, and then the question will ask, well, what's the velocity of the object when it reaches the ground? And you might be tempted to say, well, it's 0 because it has stopped at the ground. But the question is always referring to the instant the object is hitting the ground, in which case it's going to move a lot faster than when it was released. So you can think of it as right before it hits the ground or just the instant it hits the ground, but not after the object has stopped. And the other note I made here is that if you do have an object thrown downward, so it's going to need to say these words here, then the initial velocity is not 0, but if it's thrown downward, that means that the initial velocity is downward, which means it's negative or less than 0. So in case you do have one of these cases, make sure that you do give the object an initial negative velocity. Let's do an example of an object being dropped. We have raindrops falling from the clouds to the ground from 1700 meters high. What's the velocity of the raindrops when they strike the ground? Neglect air resistance, meaning we're in free fall, which we're going to be in free fall for all of these examples. In this class, we're never going to have any air resistance that we need to worry about. So let's solve these problems using the technique that we learned in the previous video of using the kinematic equations. The first technique was to write down the givens. That was the first step. So it's kind of weird because we only have one number that's given. You might be thinking, well, there's no way that I have 3 out of those 5 variables. And just to recap, the 5 variables that we talked about were delta x, which I'll write as delta y here, since we're doing vertical motion, v initial, v final, a, and t. So if we know 3 out of those 5 variables, we'll be good to go. So the 1700 meters definitely has to do with how far the drops fell, so it's going to be a delta y. But we have to be very careful when we write down delta y, because delta y is a vector, direction matters, we're going down, that's a negative displacement. Most of you will forget the negative here, so make sure, always think about which way is it going. And then you have to use the givens that we talked about in a previous slide. They're falling, that means the initial velocity is 0. It's not given in the problem, but you have to assume that they're falling from rest. And then the other one is that they're in free fall, so the acceleration is negative 9.8 meters per second squared. So even though we're only given one number here, we actually have 3 givens in the problem. We're looking for the final velocity, Vf, so we need to find an equation that has these 4 variables. So you want to go back at the table that we mentioned earlier, and I'll go ahead and scroll to it and find an equation that has delta y, v initial, a, and vf. So let's go back to that table here, and we go through and we see the first equation has these variables, which is not what we just talked about. The second equation has these, that's not what we just talked about. Neither is the third equation, but the fourth equation has the variables that we talked about. It has delta x, which in this case is delta y because it's vertical motion, and it has a, v initial, and vf. So we want to write down this last equation, v final squared equals v initial squared plus 2 times a times delta x, but we're going to use delta y instead. V final squared is v initial squared plus 2a delta y. And then the next step is to solve for the unknown. We're looking for the final velocity. So we're just going to take the square root of each side. Now, before I do that, if a quantity is 0, I do like to go ahead and cross it out just to save some time. If v initial is 0, then v initial squared will also be 0. So when I take the square root, I just need the square root of 2a delta y. And then the last step was to plug in the numbers. So the v final is going to be 2 times negative 9.8 meters per second squared times delta y, which is negative 1700 meters. Note that in this case, if you had forgotten to make the delta y negative, but you had the acceleration as negative, then you'd be trying to take the square root of a negative number, and that would make you realize, wait a second, something is off. Let me go back to my givens and make sure I wrote them correctly. Whenever you're trying to take the square root of a negative number, don't just ignore that negative. Go ahead and make sure that you have written down the correct variables, in this case, a negative here, and you see that you actually are taking the square root of a positive number because those two negatives cancel out. When I plug this into the calculator, I get 183 meters per second. Now, it does say velocity. Velocity has a direction. You know that those drops are going downward. When you take the square root of a number, your answer can be positive or negative. So in this case, you need to add the negative here because the velocity has a direction and we are going downward. I have a your turn question here. So you're dropping a rock from a high bridge. Just right afterwards, while the first rock is still falling, you drop a second rock. Will the distance between the rocks stay the same, become smaller, or become larger as they are falling? Assume the rocks don't reach the ground and don't reach terminal velocity. So I wrote these assumptions here because if they reach the ground, then the distance is going to be the same between them. And they don't reach terminal velocity. We're not going to talk about terminal velocity in this course, but maybe you had already heard of it. And terminal velocity, what that means is that actually this is when you actually don't neglect air resistance, and the air resistance is going to cancel out the force of gravity going down, and there's actually going to be no more acceleration on the object. The object will actually be going at a constant velocity. We're not going to ever have to worry about this in this course. I just wanted to mention it in case you thought they had reached terminal velocity. So they're never going to reach terminal velocity in this course. So if we think about this, let's draw a picture here. So the rock and this is number 1 here, I'll put number 1, you drop it, and you haven't dropped the second rock, number 2. So after 1 second, rock number 1 is actually over here. You haven't dropped rock number 2 yet. So this is after 1 second. What happens after 2 seconds? Well, after 2 seconds, you have dropped rock number 2. It has only been falling for 1 second, so rock number 2 is now here. It has only fallen for 1 second because it was dropped a second later. But rock number 1 has been falling for 2 seconds. You might think, oh, well, rock number 1 is over here. But rock number 1 is already moving, so in the second, it's actually going to travel more distance. It's actually going to be over here because it was already moving. And I actually calculated some numbers just in case you're curious, and I obtained these numbers by using the equation delta x equals v initial t plus 1/2 a delta y, 1/2 a t squared. Plug in 1 second into this equation to figure out how far the rocks have fallen. After 1 second, you'll get a distance of 4.9 meters from here to here. But if you plug in 2 seconds here into the equation, you actually get 19.6 meters from here to here after 2 seconds. So you can see that every second, the distance that the rock falls keeps increasing because it's already moving from the previous second. It's not starting from rest, so it has an extra distance that is traveling every time. So with this logic, hopefully you can figure out that the distance between the rocks actually becomes larger because the rock that was dropped first is always moving faster than that second rock.